Here we are in beautiful downtown Milwaukee, the campus of Marquette University. And it's a pleasant day here, very sunny day. And we're going to talk about irrotational flow, potential flow, and the Cauchy-Riemann equations. So welcome back, and we'll get started. So again, these are the conservation equations. I like to show these just to remind you of what we're doing in a global sense. And today we're going to define the potential function as exactly solving the irrotational definition. We're going to connect the potential and stream functions together, and we're going to introduce the Cauchy-Riemann conditions and this idea of orthogonality and what that means in fluid mechanics. So recall from the last lecture that we introduced rotation. It's basically rotation and vorticity are defined by del cross V. And to set them equal to 0 means the flow is irrotational. We can expand this out to show the full vector with the scalar components I, j, and k, which are the vorticity in the I, j, k directions. Now, in 2 dimensions, omega u and v would be non-zero, and w, the velocity in the u direction, would be 0, so these terms would drop out, and we'd be left just with this omega z term that I have shown here. So in 2D, the vorticity would be equal to 0 for irrotational flow, and it's basically the gradient of v with respect to x minus the gradient of u with respect to y. So in the same way that we define the stream function as exactly satisfying continuity, we can define the potential function as something that exactly satisfies this relationship here. So let's define the potential function, phi, such that the velocity, the scalar velocity u is equal to phi, the gradient of phi with respect to x, and the scalar velocity v is equal to the gradient of phi with respect to y. When we define phi in that way, we can insert it into the irrotational definition of vorticity, and we see that it exactly satisfies this definition. So what we end up with is partial squared phi with respect to partial x, partial y, minus partial squared phi, partial x, partial y. So those are exactly equal to 0. So the potential function exactly satisfies the irrotational flow criteria. And keep in mind that we haven't said anything about the viscosity, right? We're basically saying that this is just, by definition, what the potential function is. It satisfies irrotational flow exactly. So I take it as a coffee break challenge for you to extend this to 3D. Will this definition of phi work if we work with the full up 3D equation? And it's always better to work with some coffee, I think. Yeah, it's always better. All right, so let's look at the relationship between the stream function, psi, and the potential function, phi. Now, by definition, we defined them both originally with respect to the scalar quantity of velocity u, and so we can equate them to each other, partial psi, partial y, partial phi, partial x, like this, and the scalar velocity v, partial psi, partial x, partial phi, partial y. So together, that's the relationship between the stream and the potential function. And so, more simply put, we could write the relationship in this way. Now, what's the physical interpretation of this relationship? Well, first off, if the potential function exists, so if we know what the potential function is, then we could possibly find the stream function, right? So it's a relationship between those two. If both the potential function and the stream function exist, then the flow is not only irrotational, but it's also incompressible. So it implies that these irrotational flows are also incompressible and vice versa. These functions together, if you look up in any textbook, they're referred to as the Cauchy-Riemann equations. And these have a long history, and it implies much more than we want to go into at this point. But I encourage you to look up the Cauchy-Riemann equations and read this section in your book because they really are quite far-reaching. We're really just scratching the surface with what we're doing with these equations in this context. The fact that the stream function and the potential function satisfy the Cauchy-Riemann equations implies that these two functions are orthogonal. And again, this is a very deep mathematical topic that we're just going to cover here basically with regard to fluid mechanics, and I encourage you to do some additional reading on orthogonal functions. But most simply put, orthogonal functions are those that satisfy the inner product as defined here. So if we multiply the stream and the potential function together and integrate over some area, orthogonal functions will be equal to 0 over an interval from A to B. So this is defined as an inner product, so we use this nomenclature here to define the inner product. And there can be lots of inner products. This particular inner product is defined by this integral here. And if they are orthogonal, then they will be equal to 0. We could write the inner product not as an integral, but in a differential form. So the gradient of the stream function dotted with the gradient of the potential function, if that's 0, then those two functions are orthogonal. So since we know what those are, since we know what the first derivative of these are, we can perform this operation, and you can see that we would have these gradients. This is our definition of psi and the gradient of phi, and we can operate them and then insert the velocity, the scalar velocities, and we see that in fact they are exactly equal to 0. So the physical interpretation of this is that these functions are orthogonal, and a simple way to think about orthogonal functions is that they always meet at right angles. So what I've drawn here is what the stream function possibly looks like flow around a corner here. And so the potential function then always meets the stream function at these right angles and forms this mesh or this net. The physical interpretation of the stream function, if you think back several lectures ago, we defined it as the locus of points where the flow is everywhere tangent, or the locus of points everywhere tangent to the flow, to the velocity vectors. The potential function doesn't have such a clean definition. However, in 2D, we can think of it as the locus of points where the flow is everywhere normal to the function. So just, again, taking advantage of this concept of irrotation, of orthogonality, that the vectors then for this potential function are normal to the flow field. All right, let's do an example. And let's go back to this example that we've looked at a couple of times, namely flow around a corner. So I've defined it again here for you, that the velocity vector is equal to a, some constant, times x in the I direction. So this is the scalar velocity, u, minus a times y in the j direction. So this is the scalar velocity v, where a is equal to 0.3 times reciprocal seconds. So given that vector field, determine the stream and the potential function and verify that both of those functions are orthogonal. And then I'd like you to plot the stream and potential functions together. And then finally, perform that inner product integral between these two functions and show that they are equal to 0. All right, so first, let's determine the stream and the potential function. We had actually determined the stream function several lectures ago, but we'll redo it here alongside the potential function. So by definition, we have what the relationship between the stream and the potential function are, and that's essentially the Cauchy-Riemann equations. And I can take the definition of what the velocity vector component of u is and just equate it here. So that's our ax, and then equate that to the Cauchy-Riemann equation. And then I can integrate once with respect to x to solve for the stream function. I get, integrate once with respect to y to get a times xy plus some function of x. And then for the potential function, I integrate with respect to x, and I would get 1/2 ax squared plus some function of y. Likewise, I can do this for the scalar component of velocity in the v direction, the j direction, and I would get some function is that the stream function is equal to some function of ax plus some function of y, and that the potential function is then minus 1/2 ay squared plus some function of x. So I have a definition of the stream function twice here, and I can compare them, and I can see that the only way that both of these can be true is if this function x is just a constant and this function h is just a constant. So by comparing equations 1 and 3, we see that f of x and h of y have to be some constant. Likewise, if I look at the stream or the potential functions, I can see that by comparing 2 and 4, g of y and I of x must also be just a constant. They can't have functionalities of x or y. All right. So we have our stream function as a times xy plus some constant, and our potential function as equal to 1/2 ax squared minus 1/2 ay squared plus some constant. And to show that they are orthogonal, we'll show that they satisfy the Cauchy-Riemann equation. So the first one of them is this partial psi partial y equals partial phi partial x. And I insert the definition of these two functions into my equations. And I perform the operations to get ax equals to ax. So they are definitely equal to each other, and they satisfy the first of these Cauchy-Riemann equations. The second equation follows in the same way. We just write the definition of the Cauchy-Riemann equations. We insert the stream function and the potential function. We perform the operation, and we get ay is equal to ay. So the fact that this pair of functions, the stream function and the potential function, both satisfy the Cauchy-Riemann equations means that both of these functions are, in fact, orthogonal. All right, so I can use Maple to plot this. I can just pick some arbitrary value of c, and so I just picked 0 here. And when I plot the stream function in Maple, I get just that flow around the corner that we saw earlier in a previous lecture. And I'll take some time to show you guys how I did this within Maple and also using MATLAB and Fortran. During the course of this, you can look at these other lectures where I just specifically focus on using these packages. But right now I'm just going to show you the results. If I plot the stream function, the potential function, and superimpose it on top of the stream function, you can see we do generate this flow field, or this comparison of the stream and potential functions where the streamlines meet everywhere at right angles. It's quite a beautiful looking plot, really. So one of the characteristics of orthogonal functions is that they always meet at right angles. So the flow is parallel to the streamlines and therefore normal to the potential line. All right, the last part of this example is to perform the inner product between the stream function and the potential function. So this is, by definition, the inner product. And the question is this 0? If it is 0, it's orthogonal. So it's just a simple matter of inserting first the stream function and the potential function and performing this integration first with respect to x. So notice I've expanded this differential area in terms of its components, dx, dy. So this turns into a double integral. And then I integrate with respect to x first. So there's my antiderivatives. And then I evaluate this over the interval from a to b. I can do this again with respect to y. shown here. And ultimately, I get this long series of terms that is, in fact, equal to 0. So we've proven that these stream functions and potential functions satisfy the Cauchy-Riemann equations. They satisfy the inner product, so they're definitely orthogonal functions. All right, so to wrap up this lecture, we define the potential functions as solving exactly the irrotational definition. We connected the potential and stream functions together, and we introduced the Cauchy-Riemann equations and this idea of orthogonality. Next time we're going to derive the Laplace equations, and we're going to characterize it a bit. We're going to introduce boundary conditions to the Laplace equations, and then I'm going to do a quick example of a solution procedure for the Laplace equation. All right. Well, I hope you enjoyed this lecture, and we'll see you again next time. Thanks. Bye.